This one, this one, no problem. I have introduced a few more pictures here to make the problem clearer, because I read through the problem, then they are all numbers. So I draw some pictures here to make it clearer. So no problem. You're going to understand this, right? So the picture will make you understand. Don't worry. You read this example 4.3.
Find the gravitational force exerted by the Sun on the 70-kilogram man located on the Earth equator at noon, when the man is closest to the Sun. Calculate the gravitational force of the Sun on the man at midnight, when he is furthest away from the Sun. Calculate the difference in the acceleration due to the Sun between noon and midnight.
Okay. Now, let's say this blue circle here is the sun. This blue circle here is the earth. Now, the distance between the sun and the earth is actually measured from the center of the planet. So from the center of the sun until the center of the earth, that is the distance between the two planets. And it is given the symbol RS, radius of the sun, or the distance from the sun. Remember, it is until the center of the earth, right? It begins from the center of the sun. Let's say a man is standing on the surface of the earth at the equator. So he's not standing at the North Pole, he's not standing on the South Pole, but he's standing at the equator here. And the distance between the man and the sun is actually shorter by this distance, shorter by RE, right? Because the man is standing here, so the distance is not RS. The distance is this RS minus the RE here. So you see, the man is standing here. Now, at night, when the earth rotate, the man come to the other side here. So the distance between the man, which has a mass of 70 kilogram, and the earth is actually not RS. It's not the distance RS, but it's the distance RS plus another further RE, which is the radius of the earth. So if you cannot see, then we look at the picture here. We look at the picture here. Right. The green line shows the distance between the center of the earth and the center of the sun and the center of the earth. The man is standing on the surface of the earth. So he is actually not standing at the center of the earth. He's standing at the surface, on the surface of the earth. So the distance is actually shorter by the radius of the earth when you compare the distance with the RS. So the distance between this man, and the sun is actually RS minus RE, shorter by RE. Now, during the night, when the earth rotates to the other side, the man rotates to the other side, the distance between the man and the sun is not RS, it's not this green line, but it has a further distance away of RE, which is the radius of the earth. Okay or not so far? One, during noon time, the distance is shorter by RE. Midnight, the distance is longer by RE, because the man follows the rotation of the earth. So for these two cases, we are going to find the gravitational attraction of the sun on this man. We are going to find the gravitational attraction of the sun on this man. How to find the gravitational attraction? We are going to use this universal gravitational formula. So this gravitational formula tells us the force of attraction between the sun and the man, not the earth and the man, the sun and the man, is the universal constant multiplied with the mass of the man, multiplied with the mass of the sun, divided by the distance between them, the square of the distance between them. And during noon time, that distance is Rs minus Re. In this case, Rs minus Re. The force of attraction between the sun, between the sun and the man during the night still follow the same formula. The force of attraction between the man and the sun is the universal gravitational constant multiplied with the mass of the man, the mass of the sun, and the distance between them. This distance between them during the night is actually Rs plus Re. Rs plus Re. Because it's further away. During the night time is further away. So you plus Re. In the morning, he's nearer to the sun. He's facing the sun. So you minus the Re, the radius of the Earth. Okay. So far, okay or not? We use the force equals to gmm over r squared. Oh, we are going to extract these values, the distance from the sun, the radius of the earth, the mass of the sun from this given table, okay. So we look at 1, 2, 3, the third line. The third line says earth, the mass of the earth is 5.9 times 10 to the power of 24. The radius of the earth is 6.38 times 10 to the power of 6. The period, don't worry about the period. This one we want to know. The distance between the sun and the earth is 1.496 times 10 to the power of 11. Now this distance is between the center of the earth and the center of the sun. Right? So I copy down up here. I copy down the value up here. The table is, the numbers, they are very close together, right? So it's better for me to copy the number here. Yes. The distance between the sun and the earth, 1.496. So it means that over here, Rs is 1.496 times 10 to the power 11. Okay, so this is the first number I copy down. The second number is Re, the radius of the earth. So radius of the earth from the table is 5.98 10 to the power 24. Oh, the radius of the earth, this is the mass of the earth. The radius of the earth is 6.38 10 to the power of 6. Okay, 10 to the power 6. So I copy down this number, radius of the earth, right? Radius of the earth, 6.38 10 to the power 6. Next, the mass of the man given in the question is 70 kg. 70 kg. The mass of the sun. Mass of the sun from the from this here. From the table here, 1.991 10 to the power 13. Universal constant, the value is given 6.67 times 10 to the power of negative 11 Newton meter square per kilogram square. So all these numbers here, right? All these numbers from the table, I'm going to substitute inside this formula here. The formula for universal gravitational constant, the force between the gravitational force between two objects. So this I'm going to substitute inside. So first one, the force at noon time. Noon time is referring to this, the first case, right? The force between the sun and the man during noon time. So it's GMM over R square. The mass of the man is 70 kilogram. Where's the mark? Okay. The mass of the man is 70 kilogram. The mass of the sun is 911 10 to the power 30. The distance, no, this is the universal gravitational constant. The distance between them is this value here. The distance between the sun and the earth minus the radius of the earth. But you have to put a square there, right? The square of the distance. So the answer is 0.41540 Newton. So it's very small, less than half a Newton, the attraction of the sun on the man. Okay. So now we're going to look at at night. At night, the mass of the man is the same. Mass of the sun is also the same. Universal gravitational constant is also the same. But the distance between the man and the sun is now plus the radius of the earth. Okay, plus the radius of the earth. So using the calculator, you calculate, not much difference. 0.415. The other one is 40, this one is 33. So a difference of 0.001, less than 0.01 Newton. Okay, not much difference. So this will answer our question A and question B. The gravitational force exerted by the sun. Now the difference in the force, right? The difference in the force is you take the first number minus the second number, that will be the difference in the force. If you divide by the mass, that will be the difference in acceleration due to gravity. Now, what significance it has on people like us? It means that during the daytime, we are much heavier. During the nighttime, we are much lighter, something like that, due to the Earth's gravitational, due to the sun's attraction. We are further away, so the sun is not pulling us that much, something like that. Okay, so this will be the difference in the acceleration due to gravity. Yeah, you can go through this again.